6.1 Random Variables and Probability Distributions. The random variable is just the thing that we're trying to find the probability of. The probability that the answer is this number. So this probability distribution graph would show us the actual probability of each x, each value of the random variable in the sample space. So I could tell you what the probability of getting a 3 would be. It tells me the probability is 0.135. So this is just a display that tells me what the probability of each value is. There are two types of values that we can find probabilities of. One is discrete and one is continuous. Discrete means finite or countable, and continuous means sort of like a number line, an interval of values. So let's look at each of these types of probabilities and tell if it's a discrete or a continuous random variable. It takes you X minutes to finish the final. Would that be a certain countable outcomes, or is that a more of a number line type of measurement? And I would say that time is a number line type of measurement, so that is continuous. You go out for lunch X times next month. That's definitely a countable number of times. It wouldn't be on a continuum. So countable means discrete. You buy a car that gets X miles per gallon on the highway. It could get 25 or 26 or 25.7 or 25.8 or 25.75. That's more of a number line sort of thing, so continuous. And a selected group has X females. That should certainly be a countable number of things, so that is discrete. And so that probability distribution that we saw in the first slide was a bar graph because we were talking about a discrete probability distribution. That's why it was bars. Had it been continuous, it would have had to be more of sort of a line graph. The probability distribution is just the assignment of probabilities to each value of the discrete random variable or to each interval of values for a continuous random variable. Each value of the variable has to be mutually exclusive. We don't want any of those variables to overlap, otherwise it wouldn't make sense to give each of them their own probability, because we want each of those probabilities to all add up to make the entire sample space. The sum of all the probabilities in the distribution is 1 or 100%. And then if you remember that law of large numbers, as we do more and more trials, those probabilities should really start to match our actual relative frequency of our trials. So the probability distribution graph displays the relative frequency. Here's that original probability distribution. It was a distribution for number of siblings. It was definitely a discrete random variable because we should be able to count the number of siblings that someone has. That's a countable, not a number line sort of situation. And you could double check to make sure that all of these add up to 1 total. And they should also be mutually exclusive because you can't have one sibling and have two siblings. It's one or the other, never both. So if you're going to ask somebody at random, how many siblings do you have? What would be the expected value? What would be the number of siblings that you could estimate each person has? And that could be calculated just by using a weighted average. So expected value can be thought of as mean. And we can calculate that thinking, okay, well, there's a 17% chance that the person will say they have 0 siblings. There's a 36% chance they'll say 1. And if I add together all of those, giving proper weight to each number of siblings, dividing by the total probability, comes out to 1.485 on the top and 1 on the bottom. And so that would be 1.485. And so our expected value, the number of siblings that we can expect somebody to say, is about, 1.5 siblings. That's what we would expect on average the number of siblings to be. If that's hurting your head a little bit, just remember that we were taking on the top, we were taking percentages or like probabilities times number of siblings, and then we wound up dividing by percentages or probabilities. So it should make sense that in the end, our answer was the number of siblings, and we were using that formula just like we used to calculate weighted averages. Here are the two formulas of the day. This is the one that we just used actually. We took each discrete variable times its probability, and then we added them all together. This one doesn't have the whole divided by the sum of the probabilities, and that's because the sum of the probabilities is always going to be 1. So they just left that off because it's not even necessary. And then this will take you back to the standard deviation days where we find the distance from the mean, we square it, and then there's just that little extra step of taking it times the probability. So let's do an example to find mean and standard deviation of a discrete probability distribution. And the example I chose was flipping a coin 4 times. You can either get 0 tails, or 1, or 2, or 3, or 4 tails. Those are mutually exclusive, and they're definitely discrete. I even calculated those probabilities for you already, and I guarantee those add up to 1. And so the probability distribution is already figured out for us. What we're going to find is the expected value. And if you think about it, you can probably guess this already. If you flipped a coin 4 times, how many times would you expect to get tails? Well, we're going to do the math. We're going to do the formula to calculate mu. So mu is going to be the sum of each x value, each random variable, so in this first one, 0 tails, times the probability of 0 tails, plus 1 tail times the probability of 1 tail, and so on. And we type that all in and we get 2. And what does that mean? 2 tails is our expected number of tails that we would flip if we were to flip a coin 4 times. And hopefully that's what you would have guessed, since it's a 50-50 shot of getting tails on a coin. Out of 4 flips, we would expect to get 2 tails. And then for our standard deviation for our probability distribution, we're going to use this old familiar looking table I've already got set up with our random variables and their corresponding probabilities. We're going to need to use the fact that mu was 2. So each of these I'm going to take x minus 2. And then for the next column, I take that number and square it. And for the next column, I take that number, the squared number, times the probability from that second column. So for the top row, I'm going to take the 4 times the 0.0625. And for the next row, I take the 1 times the 0.25. And I did those other rows earlier. And then finally, we've got those x minus mu's. We've squared them, taken them times their probabilities. Now it's time to sum them all up. And so that's what I've got set up right here. I'm going to find the sum of all of those, and that comes out to 1. And so we're ready to calculate sigma. The standard deviation is the square root of 1. The standard deviation is 1 tail. And remember, that just describes the spread of how many tails you can expect when you're flipping a coin 4 times in this probability distribution.